So yes, I'm going to talk about one subset of the Loop platform, and the bit I'm going to be talking about is the bit that takes the raw data. If I can get the slides to advance, yes I can. It takes the raw data, which in this case is our knowledge of the geology, and it spits it out in a form that's feeding the Loop structural modeling package. And Loop structural is kind of greedy. It needs all sorts of different types of information to build a model. That's because it's clever. And in order to do this, therefore, we have to take what are our traditional forms of data, such as geological maps, and transform them in a whole series of different ways such that the data is just right for the modeling environment. And this is all still very much proof of concept, as I'll keep insisting all through the talk. And we're working on a whole series of different test areas. We started off in West Australia in the Hamersley region because the geology wasn't too complicated, but now we've stepped across state boundaries and we're trying it in a whole, basically got a demonstrator for every state and territory, although I just realized we didn't have anything for Canberra, so we might have to do that for GA at some stage. However, the idea is, I'm just going to go to a quick demo, and I'm going to bring up, if I can bring up the demo, and this is what you're going to be using a bit later on, so pay attention and see where all the buttons are hidden. So this is a map, obviously, of the Mount Isa Inlier. You'll recognize it if I move up and down. And within that area, I've selected a region of interest. It's this nice little dome that's now in the center. And if I show you the white squares, you can see the area that I've chosen. And what this code is going to do is going to take the information from the geological map and from the fault layer and from the outcrops, which are the red dots that are now hopefully appearing on your screen. And it's going to go away and do a whole series of calculations that I'm going to explain in a minute. And we're going to come back to this demo a bit later on to see what it's given us. So I'll just minimize that now and come back to the screen. And this is just showing the example I'm going to give you from the PowerPoint is actually from the Hamersley Basin in Western Australia. As I said, this was the first area that we tried it out on. So this is the area that's going into the paper that we're just about to submit. And you can see the geology has got a nice layered system with a syncline there, the Turner syncline. And the types of data that we're using as inputs into our 3D model are the geological maps, so the polygons produced by the Geological Survey of Western Australia. And you can see the stratigraphy on the right-hand side here. The faults, which are the black lines, obviously, also from GSWA. The outcrop database, so just the bedding information in this case, because that's what they recorded, also from GSWA. A digital terrain model that we're downloading from GA, from Geoscience Australia, and the Australian Stratigraphic Units database, which is also housed at GA, but it includes obviously data for each state. So these are the inputs for what we're working on. And we can think of these inputs as various different types of information. There's positional information. So where was the outcrop that we measured the bedding at? Where was the position of a fault? Where was the position of a contact? We can think of gradient information. So what's the orientation of bedding at a particular location? The DTM is fairly straightforward. How high am I above sea level? The topology I'll come back to a bit later, but it's basically looking at the relationships between different features. So the relationships between the faults and the stratigraphic units, or the relationships between the faults and each others, so on and so forth. And then there's various conceptual pieces of information that we can bring when the map itself doesn't have enough information. And in many maps in Australia, and in particular in fairly flat bits of Western Australia, there isn't much information about fault dip. So we can add that as a prior to our modeling, where the geologist says, well, based on my hunch, I think all the faults are dipping to the northeast. So that's what we're going to tell our model to do. It's not based on observables, but it's based on intuition. And to be honest, we can't build 3D geological models without putting some of this intuition in. The advantage of what we're doing here is that we're actually writing it down so it doesn't get lost. And then you can see that all of these spaghetti arrows are crisscrossing in various different ways to build up augmented outputs from our modeling. So let's look at the outputs from the analysis of our geological data. On the left-hand side, we can see that it's just putting out the contacts, which you might go, well, that's not very hard. And to a certain extent, it's not very hard. We know where the contacts are. We combine it with the digital terrain model to get the Z value. The thing that's slightly clever here is that we're actually having to work out for each polygon what the base of each contact is, because that's the contact that's going to be used to define the 3D model. So obviously a polygon is going to have contacts which are defined by faults, and it's going to have contacts that are defined by the top of the sequence and by the bottom of the sequence and by intrusions. And the code that we've written pulls apart the map in order to work out just what those basal contacts are. On the right-hand side, we've got information about the faults. And again, here we're using the mapped position of the faults, combining it with the digital terrain model to get the Z location. If there's any information in the map about the dips, we use it, but often there isn't. And we do an analysis of the relationships between faults to work out which one is younger and which one is older. So those are contacts and faults. The folds, we do the same sort of thing. We can get the fold axial trace, and from the mapped information, we can work out whether they're anticlines or synclines. One of the things that we can calculate, because we know we can estimate where the contact is, and we can estimate what the dip of the bedding is, we can actually make local estimates of unit thickness, not just apparent thickness, but estimated true thickness, which sounds like a tautology and probably is. But the idea is that we're making estimates of the thickness of the units, taking into account the bedding information that's available. And this is not just a regional calculation, it's a local one, so that we can see that there are, for example, variations along a unit in its true thickness. And that can be useful in terms of identifying depositional faults and other things of that nature. We can also pull apart the map and look at the apparent offsets. And if we assume down dip displacements, which for these faults is a reasonable assumption, we can actually calculate the local variations along a fault of the amount of offset. And again, that can be useful because variations in offset along a fault might lead to variations in the amount of damage within the fault. So the amount of porosity may change within the fault. And so it might even be an indicator of preferred locations along the fault for fluid transfer. There's other ways of calculating the fault offset just based on the stratigraphic displacement. And so everywhere where we have a fault, we can make an estimate of whether there's a 1 unit offset, a 2 unit offset, a 3 unit offset, and those sorts of things. And then the final image on the right-hand side here is telling us which direction was the downthrow side, so that we can identify which are horse and which are grabens, or where there may be scissor faults based on these apparent offsets. And in this case, it's on the assumption that the unit thickness is the same side, both sides of the fault. But as I showed you before, we can calculate that. So that's not such a bad problem to solve. Before I talked about topology, and one of the things that we started working on very early was the idea that we couldn't just rely on regional stratigraphy to work out local stratigraphy. That's because the regional stratigraphy from the regional map or from the Australian Stratigraphic Units database gives you a summary for an entire state. And what we need to know is what the local stratigraphy is, not what the global stratigraphy is, because the local stratigraphy obviously controls the 3D geology. So we've written code, and this is Vitaly Ogarko's code, that uses the geological map to look and see which units not which units should be in contact with each other, but which units actually are in contact with each other. And so this strange sort of network diagram on the left-hand side is showing you within the mapped area which units were actually in mapped contact with each other. And it also tells you why, whether they were across a fault, whether they were a stratigraphic contact, whether they were intrusive contact. And so this gives us an ability to build up the local stratigraphy. We can do the same sort of thing with faults. And so here we have all of the different faults in the area and their contact relationships. An arrow says that this fault is in contact with that fault. The size of the box, and each box is a fault, tells us how many other faults that fault is in contact with. So it gives us an idea of the importance of the fault again. And then finally, we can look at the relationships between faults and stratigraphy. So here we have rows which are stratigraphy and columns which are faults. And if it's green, it means that that stratigraphic unit is cut by that particular fault. And so again, it helps us to build up an idea of the spatial relationship, but also the temporal relationships, the time relationships between the different parts of the geological model. We can do that, and we need to do that in order to build our 3D geological models, but we can also use that information on a more metallogenic, in a more metallogenic sense. And here we've plotted on the left-hand side all of the red dots are iron ore deposits, and all of the blue dots are copper deposits. And on the right-hand side, we've got a subset of this network diagram showing the different stratigraphic units. And the numbers within the unit, within those rectangles, tells you how many deposits are found within a particular unit. And if there's a number on the arrow, it's telling us how many deposits were found within some buffer of a contact between the different stratigraphic units. So it helps us to pull apart not just the stratigraphic story, but it tells us where the mineralization is in a stratigraphic context, in a fault context, or in an intrusive contact context. So it's giving us the mineralization in the complete lithostructural framework, which is a really interesting way of looking at mineralization, at least we think so. So the idea is that we take our raw data, we feed it into our nasty code, and we end up with a 3D model that looks like this. And this model on my laptop takes about 15 minutes to build from the raw data. And the great thing about this is that if I'd have gone back and said, well, I said last time that I thought all the faults were dipping at 45 degrees towards the northeast. If I want to change my mind, I can, in 15 minutes, I can rebuild the entire model with a different assumption that the faults are all vertical. And so you can very quickly test a whole series of different models. And on the right-hand side, we're seeing the black lines of the original geological map, and the colors are the predicted geological map from the 3D model that we just built. So it gives us an idea of how well we're able to reproduce our original observations as well. But it also allows us to extract types of information such as this. And this is the displacement, not calculated directly from the map, but predicted by the 3D model. So red areas are predicted to be downthrown areas, blue areas are predicted to be upthrown areas, and the sort of wishy-washy green means essentially no displacement. So again, it's visualizing which areas are horst, which areas are grabens, which of course could have major significance in terms of our understanding of the structural, but also metallogenic evolution of the region. So let's go back to our demo, and I'll just bring up that notebook again. And if we scroll down, it took, in this case, it took 1.5 minutes to pull apart all the data and get it ready for the modeling. I actually don't know how long it took to make the model, but it was like a minute, 1.5 minutes. And we end up with a model. This has got 3 times exaggeration, and you can see all the colored vertical faults. And we've said they're vertical because I didn't know what else to say, but that's easily changed back at the beginning. And we can see all the different stratigraphic units. So in less than 5 minutes, we've been able to go from the original data, in this case, to a complete 3D model. And it's not the best 3D model that you could ever build of this area, but it's certainly the fastest 3D model that you could ever build of this area. And if we imagine that the work that Jeremy Giraud's doing on the geophysics, we can use this as the starting point for an inversion or a joint inversion of geology and geophysics, so that we can very quickly get to something that's a reasonable model without having to spend months of preparation to do the work. But it's not really the speed that's the important thing, it's the automation that's the important thing. And I'll just close that down, and I think I've only got one more slide. And so, yes, it does speed things up, but as Laurent has already said, perhaps more importantly, it's reproducible. Every time we draw the same rectangle, we get the same model. And it enforces the separation of the types of inputs into the modeling. So it's no longer a case of the geologist or the modeler sitting down with a whole bunch of information, plus their preconceived ideas of what's going on, plus the changes they have to make when the model doesn't work the first time. But in this situation, we're clearly separating the primary observations, the interpretations, the derived data, such as formation thickness, and the conceptual priors, such as the orientations and dips of faults, that are very easy to modify in order to produce new models. And as a result of that, it produces a homogeneous pathway to the inversion codes that we're working on, to sensitivity analysis. How important is this observation to the final model? Uncertainty quantification, because we can build hundreds of models with different preconceived ideas, is helping us to build models at different scales using the same data. And the work that Mark Lindsay's doing is allowing us to look at value of information. How important was a drill hole to building a model which actually reproduced all of the available data? Or could we have saved the money in this case? So, final warning, proof of concept, use at your own risk. Thanks to all the sponsors. This is sponsored by the Loop Consortium, by the ARC and MinEx CRC. And Laurent's already told you what Rick thought the workshop was going to look like, and this was my interpretation. So we're going to leave it there. I'm going to get Lachlan Gross to introduce the workshop itself, because he's the one that's put it together, so he deserves the glory for that. And I'll stop there and let people have questions.
Do we have any questions from anyone? Lachlan, I can tell you that I've got a whole bunch of little pieces of paper with numbers on them, at least.
Cool.
I've made a complete balls up of the numbers. That's the only thing, but
as long as the numbers are within the range that I said, it should be fine.
Yep. We've got a bunch of people online too, so I don't suspect everyone in the room is going to want to do. Oh, sorry. Go ahead and ask your question. Oh, wait a second.
I just got a question. How sensitive is the modeling process to errors in the topology? So you had some shape files or whatever input GIS data, and there are gaps between the map surfaces, the mapped polygons. How does that affect the modeling process?
Okay, well, there are two things there. One, if those gaps are because there's sufficient cover, then we can just ignore the sufficient cover. So if you've got a geology map that's part basement, part sufficient cover, we can just ignore the cover and that works fine. If you've got a really badly drawn geological map where there's polygons that overlap and gaps between them, then it doesn't like that because it doesn't know how to interpret a void in that sense. So you have to make the map watertight in order to be able to use this code. However, if there's gaps because of cover, that's not a problem. Obviously, there's no data where there's the cover, but it won't actually hurt the calculation.